Welcome back, everyone, to the What Are Quantum Computer series. In the previous video, we were representing bit operations with matrices, and in this video, we're going to be representing multiple bits in a quantum computer, because so far we've just been staying with a single bit, right? But now we're going to be diving deep into multiple states, right? Multiple systems, multiple bits, right? Before we do go into the video further, why don't we do a quick overview? So we're going to be understanding multi-state systems, how to normalize those multi-state systems. Then we're going to represent the linear combination as a vector in Python. Um, Obviously, we'll put that in the end, but we're going to be following that up with the tensor product with the two parts of it, and then the operators with the tensor product, and then we have two parts with that, and then the Kronecker product and the Kronecker product of our state vector, and we're gonna have some Kronecker fun in Python. All right, so understanding multi-state systems, right? So let's say if we had two qubits, right, that had multi-states, right? So we have Q1 with states 0 and 1, and Q2 with states 0 and 1, right? So these have two different states now. Q1 and qubit is now a 2-bit system, right? And each of these two systems can exist in one of two states, right? So how many total states would there be for the whole combined system of Q1, Q2 to be in? Well, if each subsystem of either Q1 and Q2 has two states, that means that the whole composite system would be 4 states. So really, when we write it out, we would have 0, 0, 1, 0, 0, 1, and 1, 0, right? So one thing that we also need to know is that these 4 states still need to obey the law of quantum mechanics. And one of those laws are being the normalization of qubits or the normalization of multi-state systems, right? So if we remember in the normalization of qubits, we had associated our states with a certain linear combination variables. So here our multiple states would have multiple combination variables. So let's say if we assign 0, 0 for x, 1, 1 for y, 0, 1 for z, and 1, 0 for a, right? Now our normalization equation would be x of 0, 0 plus y of 1, 1 plus 0, 0, 1 plus a of 1, 0, right? And our normalization condition should always be equal to 1, as stated, even if there's an infinite amount of states. So that would just be x squared plus y squared plus z squared plus a squared equal to 1. All right. So now how would we find this whole linear combination in the computer as a vector in Python, right? Of x 0, 0 plus y 1, 1 plus z 0 1 plus a 1, 0, right? Well, we would use matrices, right? And the states of our qubit systems would always use column vectors, right? If we are trying to find this linear combination, right? So we'd have our vector or an array in Python, or matrix of x, y, z, a, right? And then now, what would our second vector test matrix be? And how would we describe that system? Well, that would simply be the amplitude we're trying to find with, right? So that is what goes into the tensor product, right? So we would be having 0, 0, 1, 1, 0, 1, and 1, 0 as our matrix that would be trying to multiply with x, y, z, a, right, to get that combination. But it's more complicated than that, because what if our states, instead of being, as we had just mentioned, was instead a little mix-up of 0, 0 being x, but now we have 0, 1 being y instead of 1, 1 being y, and 1, 0 being z instead of 0, 1 being z, and 1, 1 being a instead of 1, 0 being our a, right? So now our new a here is 1, 1, and our a in in these new states is really our y in this previous states here, right? So now our states are mixed up, right? So now we need to find a self-consistent way to define the certain states of our system, right? And it always has to stay consistent with the states that are given, right? And it requires that for each subsystem, you identify the 0 state and then the 1 state. So behold the tensor product, which uses the symbol right there. And the tensor on an operation is on a vector, essentially. When you go to high level physics, you will learn more about it. But for now, um, we're going to be learning about it in here. But instead of having 0 and 1, we would have 0 tensor of 1, right? And now that you have broken your 4-dimensional spaces into 2 subspaces, either bit can either be a bit of 0 or 1, right? So now back to 0 tensor 1, we can now identify and define operators in both of our 2D subspaces. So in either of the subspaces, we can do as many operators as we want. So let's say in the cubed 0, right? Let's say if we wanted to use the flip operator, right, on 0, then we could also use something called the identity operator. Now, side note, when we apply the identity operator to a state, the same state gets returned. So literally, it's the identity of a state, right? So if we were to do the flip tensor identity, right, I being identity, the flip would act on the first bit here, and the identity would act on the second bit, right? So we would have a 2 by 2 matrix of 0, 1, 1, 0, and a 2 by 2 matrix of 1, 0, 0, 1. Right? So flip acts on this bit here, and identity acts on this bit. Right. So now when we do the flip tensor of I, or identity, on 0 and tensor 1, the flip, again, as we just mentioned, it would act on the first bit of 0, and identity would act on the second bit. So if we remember a few videos ago when we did the flip of a certain bit, so the flip of 0 would simply just be 1, right? It would be the opposite, right? And then, as we just mentioned, the identity returns the same state, right? Because it's literally just the identity. So the identity would just be 1. So now after we do this operation here, we would have 1 tensor 1, right? So this is kind of what we'd have here, right? Since we mentioned that our qubit 1 would have a state of 0 and 1, and 1 would be 0, 1, right? So now the tensor product basically bookkeeps any subsystem we are acting on here, right? Right, so the Kronecker product, right? So the idea of flipping the first bit and keeping the second bit is really implemented by the Kronecker product, right? Now here it takes the components of the first matrix and multiplies each component of it by the second matrix, right? So now how would we find the Kronecker product work out for F tensor of I? Well, we know that our flip matrix is 0, 1, 1, 0, and our identity matrix is 1, 0, 0, 1. So if we were to find the Kronecker product, we would do 0 times the identity matrix here, 1, 0, 0, 1. So 0 times 1, 0 times 0, 0 times 0, 0 times 1. So that just result in 0, 0, 0, 0, because anything times 0 is obviously 0. And then for 1 here, if we did 1 times this whole identity matrix here, it would return the same thing, right? 1, 0, 0, 1. And then you can do the same thing. So 1 times 1, 0, 0, 1. You get 1, 0, 0, 1, and then 0 times 1, 0, 0, 1, you get 0, 0, 0, right? So this right here is our Kronecker product, right? And so this matrix here is a really nice abstraction of the idea of flipping the first bit and really keeping the second bit, right? And you can extend this to as many bits as you want, right? As many Kronecker products, right? So now what we will do is we will calculate the Kronecker product of our state vector, right? So our state vector is 0 tensor of 1. So first we're going to have to do is convert our vectors to its states. So we know that 0 is categorized as a qubit of, so state of 1 and state of 0, as we had mentioned. And then for qubit, so then for this one over here for 1, it would just be tensor 0, 1, right? Now that we've converted our vectors to its states, we're going to go on to the multiplication, right, for the Kronecker product. So we're going to do 1 times 0 and 1 times 1. So that would just return 0, 1. And then we do 0 times 0, 0 times 1. So that would just be 0, 0. So now as you can see here, we have that instead of representing our vector as x, y, z, a, we have found ourselves a self-consistent way of representation, since we know that the 0 and 1 state is represented by 0, 1, 0, 0, which is a 4-dimensional vector. And as a result, that is consistent across everyone who is labeling these states, right? So now we don't need to worry for mix-ups of our states, right? So now why don't we go have some Kronecker fun in Python with the Kronecker activity? I thought that was a little funny, but yeah. But anyways, we're going to be showcasing the np.cron function, which gives a Kronecker product of 2 arrays or 2 matrices, right? Like we're going to be using the flip state and we're going to be using the identity state and find its Kronecker product, right? We're going to create that. And then we're going to represent the 0 state qubit and the 1 state qubit and find its tensor product. And then finally, what we're going to be doing is we'll be testing to see whether our operation gives us the expected state vector, meaning that they should both be the same. So why don't we head to Colab? All right, so let's go here. All right. Okay, so beautiful quantum algorithms. I'm pretty sure this was when we had left off from our operation representation with our matrices. Now what we're going to be doing is we are going to be creating our flip array and our identity array, right? And then we're going to be finding the Kronecker product of that. So first what we're going to be doing is we're going to name a variable flip. And as you know, we symbolize a matrix as an array in Python. And if anybody does not know what an array is, just go back to one of the previous videos. I think it's in the bit operations video. I explained what an array is, and the one-dimensional array, the two-dimensional array, and the three-dimensional array, right? So that video does explain it really well. So if you still need some retouch-ups on arrays, just go to that video. So we'll do flip equal to np.array. So again, remember np comes from our numpy, right? Import numpy as np. So just in case if our program does give an error, let's just import numpy as its alias np again, right? So we don't hope for any errors, right? So now we're gonna have flip is equal to np.array, and then what are we gonna have in our array, right? We're gonna have a two-dimensional array this time, right? Because it's a matrix, right? So we're gonna have two brackets, and then we're gonna have 0, comma, actually, because you know, our zero state is going to be represented by 0, 1. So we're going to have 0, 1, comma, the one state, which would be 1, 0. All right, so that's our flip. And then our identity is, again, np.array. Would be the same, two-dimensional vector. And here it would be our identity of, so it would be 1 and our state of 1 and our state of 0, right? So we would just have 1, 0, which is our state of 1, 0, 1. All right. So now how do we find the Kronecker product, right? So what we're going to be doing is we're going to be doing flip ID, right? It's just the Kronecker, and we're going to be using a function in NumPy, the NumPy library called np.cron. What does np.cron do? Well, it simply just takes the Kronecker product of two lists or two arrays, right? Sorry, two matrices of flip and identity. So I'm guessing you can already guess what our parameters are going to be. It's going to be flip and identity, right? Now, one thing to note is we can't have something like identity and flip. It's not interchangeable. We need to make sure what goes in what place. As I had mentioned, we're going to be multiplying each component of the flip matrix by all the components in the identity matrix, and that's what the parameters are important for here in np.cron. So we do not want to mess that up, do we? Right? And we're just going to say that this is finding the Kronecker product of the flip matrix and the identity. All right. Now that we've done that, what we're going to be now doing is we're going to be representing our 0 state and our 1 state, and we're going to be finding the Kronecker or the tensor product of that. All right. So what we're going to do is we're going to define a new qubit, q1 is equal to np.array. We're just going to have it as a simple one-dimensional array, right? Because it's just a simple row with 1, 0, right? State of 1. Oops, that is inside the bracket. State of 1 and state of 0. And q2 is equal to np.array. This time, that'd be 0. All right. So basically, here's what we have, right? So qubit 1, which is in the 0 state, is represented by 1, 0. And qubit 2, which is in the 1 state, is represented by 0, 1. All right. Now we need to find the tensor product of it, or the Kronecker product, right? So we're just going to have our new matrix as q1, q2 equal to np.cron. And q1, q2. Oh, one thing to do before we do run this, why don't we quickly take a look at our flip ID, the Chronicle product for flip and our identity. If we run this, oh, we don't want to. We want to also make sure to print this one. So flip ID. We run this. Boom, we have 000, 10, 01, 1001, 000, right? And this is kind of familiar with right here, our Chronicle product of these two matrices, right? Our flip matrix and our identity matrix, right? So if it should look like this Chronicle product matrix here should look just like this matrix right here, right? Now moving on to our 2 qubits. Now that we have found the Chronicle product of it, we just need to print it. So we're going to print Q1 and Q2, and if we run that, we have 0, 1, 0, 0. And if this brings back anything, if we go over here, remember our state vector 0 tensor 1, that was just the Chronicle product, and we had 0, 1, 0, 0, right? X, Y, Z, A. And we didn't have to represent what XYZA was, right? We found ourselves the self-consistent wave representation, right? Since we knew that 0, 1, 0, 0 is a four-dimensional vector, right? So now what we're going to be doing is we're going to be testing whether to see if our operation gives us the expected vector state vector. So what we're first going to be doing is we're going to be map muling. Remember? So does anybody remember what map mule is? It's the matrix multiplication function, right? We're going to be map muling a flip ID, and Q1, Q2, both Chronicle products, and really it should just represent the state of one tensor of one. All right. So we're going to do print np dot map mule, and then flip ID. Q2, and again, this just represents state one tensor. Now we're going to be testing to see whether our operation gives us the expected state vector. So we're going to be doing print Chronicle product of np.array. So 2 arrays of 0, 1. So let's just put there, which is the one state, remember? 0, 1. One state. And comma np.com 0, 1. All right, both of our basically both of our one states, right? So then if we run this, oops, I know what happened. This should be an array. We cannot ever forget the brackets. Ooh, what happened here? Oh, I think I know what happened. Okay, so just that. Okay, yeah, boom. All right. So now we have tested to see that our operation does give the expected state vectors of 0, 0, 1 and 0, 0, 1. All right. So that would simply really just be our x, y, z, and a, right? Our amplitudes, right? So even though we did have a mix-up of our systems, right? Our states, right? We still got our expected state vector, right? So that's really what we were trying to find. Other than that, I hope you guys had a fun time today, and I will see you guys all later. See you later, folks.